This is topic 1.7 for AP Precalculus on rational functions and end behavior. A rational function is simply the quotient of two polynomials. The rational function is actually in the form of y is equal to f of x over g of x, where the f of x and the g of x are both polynomials, and the g of x, which serves as your denominator in here, should not be equal to 0. Now, as a rule of thumb, I would like you to remember this, that when you're going to divide a certain number by a 0, okay, that's going to be undefined. Therefore, we are saying that in rational functions, the denominator should not be 0. Now, look at the word that is formed in here. It's going to be no. So that's going to be a cue for you that do not divide a number by a 0 because it's going to be undefined. On the other hand, if you're going to divide 0 with any number, then this is because it's going to be 0. So that is totally mathematically defined. So please remember these two keywords maybe in this lesson for rational functions. So the following are all examples of rational functions. Here are your rational functions. If you're going to look at them, they're actually made of polynomials. End behavior of rational functions. So let's look at the end behaviors of rational functions. The end behavior of rational function is actually determined by the leading terms of the numerator and the denominator. Okay, keyword, leading terms of the numerator and the denominator. So let's look at case 1. The leading terms have the same degree. Okay, so that means that the horizontal asymptote that's going to be formed in here is going to be the ratio of the leading coefficients a over b. So if we're going to be looking at the end behavior of this situation, it means to say that on the left side of your function, the limit as x approaches negative infinity of f of x will be the ratio of that a over b. And also with the right side, the limit as x approaches positive infinity of f of x is equal to the same a over b. So let's look at case number 2. In this case number 2, here the numerator is lesser than the denominator. So that means that the result is a horizontal asymptote where y is equal to 0. So if we're going to look at the behavior in a limit notation, it says that the limit on the left side, well, let's read it, as x approaches negative infinity of f of x is equal to 0. Now for the right side, okay, we're going to say that the limit as x approaches positive infinity of f of x is equal to 0. So now let's look at case number 3. This is where the numerator dominates the denominator. That means that the numerator is greater than the denominator. The very first thing that you have to remember here is that the horizontal asymptote doesn't exist. Okay, it means none. Okay. Note, if the degree of the numerator is exactly 1 more than the degree of the denominator, then f of x has a slant or oblique asymptote. Now, I would like you to understand it very carefully that it's just like the case 3 where the numerator is greater than the denominator. The only difference is that this is exactly 1 more than greater than the denominator. So we're going to have n plus 1 greater than d. Now, the slant asymptote is actually found by using the linear equation y is equal to mx plus b. Example 1. Determine if the following rational functions have a horizontal asymptote, slant asymptote, or neither. If the function has a horizontal asymptote, write the equation of the asymptote. Letter A, let's look at this one. Letter A. So what's the first thing we can notice in here? The numerator's degree and the denominator's degree are the same. So they have same degree. Okay, that means that the numerator is equal to the denominator. Therefore, the horizontal asymptote here is just going to be the ratio of the coefficient, which is y is equal to 3 over 5. Okay, so look at it this way. Okay, it's just like getting the f of x. Just get this part. That's going to give you 3x squared all over 5x squared. Cancel x squared both, and what's left is going to be 3 over 5. That's what we meant. That's the limit of it. Okay, letter B. Okay, so in here I can see that the numerator is less than the denominator. Yeah, the numerator is less than the denominator. So the horizontal asymptote in here is going to be y is equal to 0. Okay, so let's look at the next. So what did you notice in here? The numerator's degree is higher than the denominator by 1. So we can say therefore that the numerator plus 1 is actually greater than the denominator. So if this is the case, we're going to create a slant asymptote in here. Okay, SA. I will just put it at SA for the next. Okay, letter D, let's look at it. Now let's see, the denominator and the numerator has the same degree. So the numerator is equal to denominator. Therefore, the horizontal asymptote is going to be the ratio of your leading coefficient, which is actually 4 over 8, and 4 over 8 can be reduced to 1/2. Okay, that's the answer to that. Okay, the next, we can see in here that the denominator dominates. It means to say that the numerator is less than the denominator. Therefore, our horizontal asymptote is going to be 0. Okay, next again. Now, I would like you to disregard negative for now. We're just looking at the degrees in here. So we can observe in here that the numerator is less than the denominator again. Therefore, our horizontal asymptote is going to be y equals 0. Example 2. Write limit statements to describe the end behavior of the following rational functions. Letter A. Okay, so we notice in here immediately that the numerator and denominator's degree are the same. That means that the numerator is equal to the denominator. It means that our horizontal asymptote is going to be the ratio of numerator and the denominator's leading coefficient. So let's see in here. So we're going to write the limit statement as x approaches negative infinity of f of x is equal to 2 over 6. But 2 over 6 can be reduced to 1 over 3. Okay, that's the answer. For the right side, we can say the limit as x approaches positive infinity of f of x is equal to the same thing. That's going to be 2 all over 6, which is going to be lowered to 1 over 3. Letter B. Okay, so here, what did we notice in here? Look at the numerator's degree and the denominator's degree. So here we can see that the numerator is less than the denominator. So what can we conclude with that? It means to say that our horizontal asymptote is going to be y equals 0. Now we're going to write the limit statements. In here it says that the limit as x approaches negative infinity of f of x, oh no, not f of x in here, it's going to be g of x. Okay, g of x is equal to 0. Same with the right side. the limit as x approaches positive infinity of g of x is equal to 0. Okay, so let's look at letter C. So if you're going to take note of this, the numerator's degree is higher than the denominator. Okay, the numerator is greater than the denominator, so therefore there is no horizontal asymptote for here. Okay, so if we're going to write the limit statement as x approaches negative infinity of negative 3x4 all over x cubed, that's going to give me negative 3x only. Now remember very carefully that all the numbers in here will be negative numbers. Okay, so that means that it's just like you are going to be multiplying negative 3 times negative infinity, so the result of that is going to give you positive infinity. Now on the right side, the limit as x approaches positive infinity of negative 3x4 over x cubed is still going to give me negative 3x. But I would like you to remember that the values of x in here are all positive. So this is like negative 3 multiplied by positive infinity. That's going to give you negative infinity. Therefore, in here on the right side, it's going to be negative infinity. So that's going to be the answer to that. If you're given a graph and they're going to ask you to state the limit statements, you can still do that for as long as everything is provided in there. Now, in this case, we are provided with the horizontal asymptote. What is our horizontal asymptote here? Horizontal asymptote is y is equal to 2. Okay, so in here, if we're going to state the limit statements, then on the right side, okay, I'll start with the right side, the limit as x approaches positive infinity here. Positive infinity of f of x is equal to 2. For the left side, I can also say that the limit as x approaches negative infinity of f of x is equal to 2. Okay, next, the letter E. Now, here I would like you to be very observant because in here you can actually see two asymptotes, two vertical asymptotes, and one horizontal asymptote. What we are interested in here is the asymptote horizontally. So if we're going to speak of its limit statement in here, we can say on the left side that the limit as x approaches negative infinity of this graph, it's not named, is equal to negative 1. On the right side, we can also say that the limit as x approaches positive infinity of f of x is equal to negative 1. Okay, as simple as that. Okay, so let's look at slant asymptotes. If the degree of the numerator is exactly 1 greater than the degree of the denominator, a rational function will have a slant asymptote that is parallel to the ratio of the leading terms. So I would like to look at the keyword in here. Always remember, it's like a case 3 that we have studied earlier. But here, the degree of the numerator is exactly 1 greater than the denominator. Okay, there will be a slant asymptote. So here, we can always look at the asymptote that is parallel to the line of y is equal to ABX. Okay, example 3. Here, which of the following rational functions has a slant asymptote parallel to the line y is equal to 1/2 x? Now, look at this one. 1/2 x is actually linear in its very nature. Okay, so let's see our options in here. So for the first option, we can see that the numerator and the denominator's degrees are the same. So that's going to yield 1/2. The x is missing. Okay, for option number 2, this is the numerator is less than the denominator. Okay, I guess it's not. What else? What about this one? Third option. We can say that the numerator is actually greater than the denominator, and it's actually exactly 1 greater than the denominator. So let's try to look at it. So let's say h, so that's going to give you x squared over 2x. That's going to be giving me, cancel that, and then that's going to be 1. It's going to give me 1 over x. Okay, what about k of x? Here the numerator is greater than the denominator, but it's also going to yield 1/2. Now let's look at it. So you say x 4 over 2x squared, that's going to actually give you here is square, and this is going to give you x squared over 2. I guess it's not. So with all of these choices, what is the best choice that we can see in here? All I can see here now is only choice or option number 3. So that is the answer to that. This is all for topic 1.7 about rational functions and end behavior. If you find this video helpful, share, like, and subscribe. Thank you very much.